Okay, quick review of flux in general. If you watched the first video, you know that flux in general refers to flow, and so flux in general could be the measure of the flow of anything, the measure of the flow of radiation from the sun, the amount of fluid that flows through something, the amount of radiation received on a surface, the amount of rain that hits something. And in this case, we're going to look at electric flux, and it means the amount of electric field that lands on a surface. Keep in mind, however, that the electric field isn't a moving thing, it's static. So when we have a charge and we draw electric field lines, it looks like the field is flowing out, but no, the field, this just represents the field, and there's arrows because the direction of the field is out. But it's static. But this picture could easily represent a light bulb radiating light. And so what we want to do is measure the amount of light or the amount of electric field that passes through any given surface. Just a quick review of a few kinds of fields that we've seen. I just erased the field due to a point charge. That radiates in all directions. And so I hope you understand it follows the inverse square law. It gets weaker as 1 over r squared. If we have a charged rod, the field along the rod in this direction is going to appear to be uniform, but only at the ends it goes out. So as you move away from here, it looks like it's uniform, right? Because the lines aren't spreading out. But if we take this rod and we rotate it 90 degrees, so we're looking down the axis of the rod, what do we see? Down the axis of the rod, it does spread out. So as we move away from a rod, it doesn't get weaker as 1 over r squared. It gets weaker as 1 over r. And there's an equation for that, the electric field due to a rod. You can look it up, but it's 1 over r, because it only spreads out in this plane, whereas in the other plane it doesn't spread out. And the final kind of field is the field due to 2 electric plates, which gives us a uniform field, and we've seen that. So if we had a square plate on the bottom that was positively charged and a square plate right above it that was negatively charged, the field lines would go from the positive to the negative plate, and they would all be evenly spaced. And in the space between the plates, there would be a uniform electric field. Only at the edges would the field be rounded, right? And so this is the way we get a uniform field, and we've seen lots of uniform fields, and that's the way it's created. So it's good to know all that. So when it comes to calculating the electric flux that goes through a surface, for a simple case such as this, where the field is uniform, the area element that we're calculating the flux over is flat, and so the angle between the flux and the area element is a constant angle. We can get the flux by this simple equation. 3 things determine the flux: the E, the A, and the theta. And it's easy to see how those 3 things are the important factors. It's totally logical physically that these 3 factors would determine the flux. So here are some good visuals for seeing this. So here we have a field, and we have an area element that's the same area. But when the element is facing the direction of the field, then we get more flux than if it's facing in a different direction. And notice, I should have mentioned that on the last figure. Don't forget this important point, that the angle, that we're talking about is the angle between the normal to the surface, perpendicular to the area. So an area is always, the direction that an area is facing is the vector representation of that area. So we always draw a normal, a perpendicular line to the surface to represent the direction of the area, and then whatever the direction of the field is, the angle between the E and the A, where the A is perpendicular, is the angle you want to measure, not this angle to the plane. And you're going to, if you're not careful, you'll get confused about what angle to measure. One of the ways to not forget is that the maximum flux, like in this case, is when the area element faces either in the direction of the field or opposite the direction of the field. And that if we rotate this by 90 degrees, so it's facing this way, none of these field lines will go through the surface. And so the cosine, knowing that the cosine of 0 is 1, that's how you get maximum flux. So just be careful that you always measure the right angle. So just to summarize the EA cosine theta, here's an E that's very strong. The field lines are close together. But if we make the area smaller, there's fewer field lines, fewer electric field passes through the surface. So clearly the area is directly proportional to the flux. The field strength, though, also is directly proportional to the flux. So you see the number of field lines that go through. That is the indication of the electric flux. So here we have 6 lines going through this area, but only 4 lines going through this area because it's smaller. So it's important to get that concept that you can judge visually, conceptually, the amount of flux by counting field lines. More field lines go through here than here, and if twice as many go through here, then there's twice as much flux. The other thing is the angle. If we take, this doesn't show it so well, but if we take the area element and turn it at an angle, obviously, well, this shows it actually. If we rotate this to 45 degrees, and since it's the cosine, if this is 45 degrees, it's going to be the cosine of 45. Whatever this flux is, this is going to be about 70% of it because of the cosine. Okay, so the EA cosine theta works fine if the area is flat and the field is uniform and you have one angle. But supposing here's a uniform field but a curved surface. So the field hits the surface, right, normal to the surface here, but here it hits it at an angle. So if I wanted to calculate the electric flux at this point, I would take a little area element, and this is facing this way. So that would be the A vector, and the E vector would be this way, and I would have an angle. So that you can see in a case like this, in a case like this, we have to use calculus. So if I wanted to calculate the field, let's just say we have, doesn't show the field, but supposing this is a situation where the field is all straight up through this curved area element, we would have to go through little dA by little dA, and each dA that we drew, whether it was here or here, would have a direction normal to that dA, and then the field angle would be that, and it would vary over this surface. Every other dA would have a different angle. And so the only way to solve that problem is to use calculus. And the final thing, actually 2 more things. Supposing we have this flat surface element, but the field isn't uniform. Supposing the field is not uniform, does this. Now we're going to have the same problem. The field, as it passes through the area, wherever it's passing through, it's at a different angle. And so once again, we have to use calculus. But the final thing to remember, and you'll see it on the equation sheet, is that this relationship of two vectors times, two vectors times the cosine of the angle, the EA cosine theta, can be written as the dot product or the scalar product. If you haven't seen this, you're seeing it now. This is a vector calculus notation. And the E dot dA, the dot, it's called the dot product because it's a big dot, and it's a scalar product because you multiply two vectors, E times A, and get a scalar. By definition, E dot A is the magnitude of E times the magnitude of A times the cosine of the angle between them. And so on your equation sheet, when you see this equation, you're going to see the integral of E dot dA, two vectors dotted into each other. That's the shorthand notation for this equation. So in summary, the three factors that determine the amount of flux are the field strength, the size of the area, and the angle between those two vectors, where the area is always measured normal to the surface. So in almost no case, I think in no cases this week do we actually do an integral. We'll see cases where we can just do the simple EA cosine theta, which keeps us from actually having to solve an integral. Okay, so that's the background of electric flux.